When I was 12 years old, a major hurricane hit our county and sliced an island in half about 20 miles from where I lived at the time. From catastrophic dam failures that leave houses hanging off a cliff, to the majestic 1,000-foot cliffs of the Grand Canyons, to the ditches on my construction site, the same forces of erosion act at every scale, cutting away the earth in one location and depositing it in another. When I was 12 years old, a major hurricane hit our county and sliced an island in half about 20 miles from where I lived at the time. We will use the historical imagery on Google Earth to trace the patterns of erosion and deposition over the last 20 years. Through that, we'll gain additional insight we'll apply to rewind history at the Grand Canyon and interpret that landscape according to a new model, according to a new paradigm. Is it possible to understand the Grand Canyon as largely formed during the flood of Noah as described in the Bible? One major event that surpasses the scale of anything seen before or since. An event that slices through the landscape that was before, eroding the landscape that then existed, depositing it largely in its current form. To be shaped by the subsequent events, yes, but understood from the perspective of the scale of the events and not purely by adding time, by imagining the current processes extended out over millions of years. My name is Josh Peterson. I am a professional engineer with 10 years' experience in water and wastewater infrastructure. And about 3 months ago, I was doing an inspection on my construction site, and the patterns of erosion and deposition just jumped out at me. In the moment, I had to pull out my phone and capture the scene, and I'm so excited to walk through 5 steps that will open your eyes to see the patterns. At the end of this episode, we'll jump into Google Earth. We'll apply our new understanding to see a real-life example and a case study. The first step towards rewinding history that I want you to understand are the patterns, specifically the patterns of erosion and deposition. The main idea here is that by reading the patterns, we can rewind history. I've divided up the screen here into 3 areas, and we're going to look at the clues in these 3 areas, the textures, the particle sizes, and the slopes, to understand these patterns. At the top there, in the green, we have what represents the mountains. Rainwater in the mountains where the slope is steep picks up sediment. That's erosion, the source from the mountains. Water carries it downhill, and as it slows down in the valleys, it loses energy and it drops that eroded sediment into an easily recognizable pattern. That pattern we're going to look at next now in step 2, which I've labeled fans or deltas. The main idea here is that we can recognize that pattern of deposition with some clues. Once I show this to you, you'll be able to see it everywhere you look, not only in this picture, but also as you're driving down the road. These clues, first of all, I want you to notice the curved leading edge. Notice how it's smooth. The next clue is the triangular shape, which is called a delta after the Greek letter. Notice the pointy end is towards the erosion source. It's towards the mountains. Notice the gentle slope as compared to the mountains. The mountains are steep. These fans or deltas have a shallow slope, a gentle slope. This pattern we see throughout this photo, to the left and to the right. The same gentle curved leading edge. The same triangular delta shape. Again, the pointy end is towards the mountains, towards the erosion source, the same gentle slope. And when we look across this photo, we can see that same pattern everywhere. And also, we're going to use tools like Google Earth or the USGS National Map Viewer, where we can see these exact same patterns. The same curved leading edge, the same point towards the mountains, the same gentle slopes. Notice how this pattern is repeating over and over and over again. And that idea of repeated patterns is step number 3, which we call fractals. The main idea of fractals is that it's the same repeated pattern at different scales. Here on the construction site, we have dozens of these. I'm highlighting a few here, but there are many more that I'm sure you can find throughout this photo even. As a reminder, what does the fan pattern demonstrate? Was it erosion or was it deposition? Yeah, it's deposition. These fans represent deposition. And notice that blue fan that I've highlighted there. Notice how that's much bigger than all the others that I've highlighted. But it has the same characteristics, the same clues that we saw, that curved leading front edge, pointing back towards the source of erosion. I want us to see here the concept of the order of magnitude. These fractal patterns repeat on a large scale and a smaller scale. And that's why it is so important for us to recognize the fractal nature of geology, because when we model erosion and deposition according to a fractal model or a fractal paradigm, we gain new insight into the natural processes that create these landforms. And we can apply this understanding to large-scale features on a continental scale. But I'm getting ahead of myself. We're only on number 3, and we will return to the fractal model in more detail later on. First, we have 2 more quick steps that we need to review. I'm going to clear the screen, and we'll move on to step number 4, which is the pattern of erosion. Having cleared the screen, what's the next feature that jumps out at you? Probably even more than the fans or the deltas that I already highlighted. I've added some arrows here, and we're going to pause for a moment so that you can observe the differences between the shape and form of the fans that we just looked at and the shape and form of the erosional features. What textures and shapes do you see in erosion? How is it different from the gentle curved leading edge that we saw in the fans? I've picked one to highlight for our observations, and we'll look at it here together. What do you see? Notice the sharp ridges to the left side and to the right side. Notice the shape of the channel. How does the squiggly erosion channel compare to the gentle curve at the front edge of the deposition in the fan? Notice how the channel is wide at the mouth and gets narrower upstream. Notice where the channel is in relation to the fans. Remember that large fan that I circled in blue earlier? Notice how this erosion channel slices through the leading edge of the large fan. Notice how at the end of the erosion channel there's another fan, which is smaller than the large fan, but on the same scale as the erosion channel itself. And that pairing of erosion and deposition is the real insight that I want you to understand here at step number 4. The main idea, the principle of incommensurability, which I learned from Fractal Woman, my favorite YouTuber. I put a link to her website article in the description, in which she describes the concept in detail, and she lists over a dozen examples. This idea of a conjugate pair, 2 principles that are conceptually related but opposite or inverse. Erosion is not deposition, and deposition is not erosion. A couple of the examples that Fractal Woman gives for this principle are darkness and light, or silence and sound. But the principle of incommensurability includes more than just the conjugate pair. It also leads to the recognition and understanding of emergent properties. Emergent properties are revealed between the conjugate pair. So back to Fractal Woman's examples. The conjugate pair of darkness and light. What emerges at the interface between darkness and light? If we have only light, then the light is blinding. But if we have only darkness, then the darkness is also blinding. But at the interface between light and darkness, we have, as she puts it, illumination. Or we have sight. What emerges between silence and sound? I'll spare your ears from the chaos of sound. But between silence and sound, we have hearing. We have communication. Bringing this back to geology, what emergent property is revealed between erosion and deposition? Between them, we get the landscape. When we look at these landscapes, we can ask, where did the soil come from? Where did the sand that makes up the sandstone rock come from? Every rock, every hill, every riverbank and riverbed has been shaped by the process of erosion and deposition. When it erodes, where will it go? What used to be there that has already been eroded away? This interplay between erosion and deposition is the most foundational tool for exploring and understanding how the Grand Canyon formed, for example. The rock layers that we see now exposed at the Grand Canyon are made up of sediment. Sediment which was previously eroded from somewhere else, and then deposited on the Colorado Plateau, and then again was partially eroded away to leave the beautiful and terrifying cliffs and curves that we see today. That sequence of erosion and deposition and erosion and deposition is what we're going to look at next. That's step number 5. Sequence and scale. The main idea is that the sequence and the scale of these erosional and depositional patterns allow us to reconstruct history. The clues are, which came first? Was it the erosion, or was it the deposition? How big of an event would be required to erode or to deposit? And each landscape is different and unique. But by understanding these patterns of fans, these smooth edges in the triangular shape, the patterns of erosion, the sharp edges, the curved nature, and the sequence of erosion leading to deposition. I'm going to stop this animation now so we can talk through it. When we say, which came first, we have at the top that large fan that I previously pointed out in blue, the large scale. And if you look there, down at the front, down at that smooth edge of deposition, what do we see? We see erosion. But we see many channels leading out of it. Notice the scale. Those channels leading out of it are small in relation to that large fan. Now, where are these erosion channels leading? Each one of them ends in its own fan at a smaller scale. By following this sequence, we can say, what came first? First, we had the large fan. Then we had erosion. While we had that erosion, we had the deposition of these next fans. And again, from those fans, we have erosion. And erosion leading again to deposition. So we can trace back the combination of these processes which together shape the landscape, and we can gain insight into the past. Now that you understand the tools that we will use to rewind history, it's time to jump into Google Earth and check out the case study from Hurricane Charley, a Category 4 hurricane that struck the Gulf Coast of Florida in August of 2004. At the time, this was the second most costly storm in history, and the storm was so powerful that at the point of landfall, it carved out a channel 1,000 feet wide through the island of North Captiva, literally cutting it into 2 pieces. As I zoom in further on the specific area where the storm hit, I set the historical imagery back to 1999, which is the most recent date for the imagery of this island before the storm. And as I advance to the 2004 image, you can see the dramatic breach through the island. The force of the hurricane ripped it in two, eroding new channels through the island and depositing that sand into those fanned formations behind. As I trace the outline to capture this initial condition in 2004, I want you to look for the patterns that we discussed earlier. What were the clues when looking for the fans? That curve on the front edge, with the overall triangular shape pointing back to the erosion source. The fact that we have 3 parallel and somewhat overlapping channels makes it a little harder to distinguish, but I'll highlight the patterns for you. First, the delta-shaped fans. Notice pointing back towards the channels. Now I'll highlight the channels. See how they have that squiggly branching form? And notice, what do we find at the tips of each of those smaller branches? Particularly on the lighter aqua highlight to the left. I'll highlight a few of these smaller fans now. And do you remember what we call these variations on the pattern? These self-similar shapes, repeated at different scales? Those are called fractals. And as we advance the historical imagery to the next year, 2005, I want you to pay special attention to the fractal nature of the landform and how it continues developing. Notice the variations on the pattern of erosion and deposition as I trace the outer edge here on the 2005 image. The orange areas represent the next iteration of the conjugate pair of erosional and depositional forces. The overall shape that the hurricane carved into the landscape, traced out in yellow, remains largely unchanged after 1 year. We can see that over time we're adding detail compared to the previous step. Those orange fans extend out like fingers, adding to the complexity of the landscape, without really changing the previously traced yellow boundary to any great extent. As I advance the year again to 2006, pay attention to the difference again as I trace. Do you notice those same patterns? Do you see how the normal weather patterns are continuously acting through erosion and deposition to sculpt the landscape? How does the scale of these yearly changes compare to the scale of the landscape-defining changes that occurred on one day during that landscape-defining event known as Hurricane Charley 2 years ago? As we advance again to the next year, 2007, just 3 years after the hurricane, we see at the leading edge there's almost no discernible change from the year before. The scale of the changes is so small compared to the previous year that from the satellite view we can't even see them. Along the shoreline, we do see a definite change in the channel that passes through. In fact, remember how the initial hurricane impact cut a 1,000-foot wide gap defined by 3 main channels? What do we see now? Pay close attention to that area as we advance 1 more year. Notice how the coastline there in the front has completely healed over. The 1,000-foot wide scar in the landscape has now healed over through the normal, everyday processes at work on the coastline. Though the island had been split in two by a major event, the normal processes have now healed and connected the island back together. But even though the channel has closed, the effects of the hurricane are still clearly evident, not only in the fan-shaped deposits behind the island, but also in the remnant form and shape of the channel. Looking at the aqua blue tracing off the backside of the island, we see a little more change from the previous year, the channels becoming more defined, the fans extending out at the edge of those channels, but again, the overall shape of that whole area is pretty much the same. We're getting more details molded into the landscape at the small scale, but still, the major form was defined by a single, one-day event, now 6 years previous. As we advance forward again, what changes do we see in this next year? At this point, it's pretty much a static image. I'll advance quickly through the remaining years so you can see that the landscape now remains essentially static. And this is a really great illustration of the fractal principle. We have the same conjugate pair of erosion and depositional forces on display, sculpting the landscape on a large scale from a large event, down to the finer detailed scale from everyday weather patterns. The landscape was shaped initially by a large event, a major hurricane, acting at a scale well beyond what had been seen over the past decades, and it made one landscape-defining change. Then, year by year, The edges have been molded and shaped by everyday processes until, just 6 years after the major event, the scale had been reduced so small that we can't even detect them on the satellite view. And I want to compare how well the fractal model matches what we actually observe in the actions of nature. We're going to start here in 2004. The hurricane has come through. It's just reshaped the landscape. Major changes on a scale far above the days, the months, the years, and even the decades before August 13th, 2004. The hurricane slices through the island, cutting new channels, depositing the sand behind it. 1 year later, we see that initial deposit, that red, has been reshaped somewhat. We see new detail, but still matching the same patterns of erosion and deposition that we recognize. Advancing again, the overall shape, that red, that initial event, remains largely unchanged. We continue to add additional detail from the normal course of changes, the afternoon thunderstorms, the normal working of nature. The changes become smaller and smaller. And eventually we get to the point where it doesn't matter how much additional time we add, the changes are at such a scale that it has almost no impact to what we see. Now compare this with the uniformitarian model of historical geology, where they say the present processes are the key to the past. If we were to add an infinity amount of time, the present-day actions of nature would never get us to the pattern that we see here. It took an event on the magnitude of a Category 4 hurricane to overcome these day-to-day patterns, to overcome the shoreline that's naturally developing here, to wash out a channel and deposit the sand on the backside. The standard geologic model does have the concept of 100-year floods or 1,000-year floods, but they miss the significance for the uniformitarian model when trying to go back into history and explain the origins of the natural world by simply adding time. But when we look at the landscapes of the Grand Canyon, for example, we need to re-examine that landscape through the understanding that the order of magnitude of events is more significant than the duration of the event. Here on North Captiva Island, one event, one day, Hurricane Charley sliced this island in half. One event opened up a channel and moved vast quantities of sand compared to the combined effects of the 20 years since 2004. Over the first couple of years, the first few iterations in the fractal model, we observed a noticeable and measurable change, but after just 6 years, the scale had decreased to the point where it was not detectable in the landscape. And this is where the fractal paradigm really shines, modeling these actions of erosion and deposition in geology according to the fractal paradigm, where we consider the scale of the event, gives us a new understanding and insight into interpreting the origins and history of landscapes around the world. So this is the insight that I want you to take away from this case study of Hurricane Charley. The insight is that we need to be thinking in terms of scale, in terms of the order of magnitude of events, as we try to unravel the mystery of how things like the Grand Canyon came to exist. Time is not enough. Stay tuned as we dig into that over the next episodes. I'm also going to be revealing a discovery that I've made that has implications on the understanding of the Ice Age. One defining landform that comes up in the context of the Ice Age is drumlins. This unique feature that's understood to have been formed in the context of glaciers. I've discovered this identical landform in an environment completely different from that of glaciers. And I'm going to reveal that in my next episode. But first, just this week, while exploring in Fractal Woman's tool to build my animation, I had an insight on the topics that she discusses on her channel. So before I get to the grand reveal of my discovery, I'm going to try and slip in a quick video especially for Fractal Woman. I'm going to briefly show you a tool that Fractal Woman created, and which I use to create the fractal animation that I've used throughout this presentation. This is on her website, and I'll put a link in the description. Stay tuned, and thanks for watching.